is Daniel Britt, and he's going to give us a cautionary tale about volatile-rich carbonaceous chondrites.
Okay, well, thanks for sticking around. This is something completely different. I'm going to talk about carbonaceous chondrites, which are of interest for as human exploration targets and also for ISRU. But why should we care about these guys? Well, although it's hard to see all the details here, there are two critical things: carbon and water. We tend to need that. If you look at, these are volatile-rich carbonaceous chondrites. They have up to 17 weight% water. You get very little water and very little carbon in any of the other meteorites. So asteroids, the parent asteroids of this stuff, are interesting targets. So these things are sources of water, OH, and organics. They're largely composed of low-temperature compounds. They're typically highly porous. They're typically weakly bound aggregates. So I've held carbonaceous chondrites in my hand that were essentially dirt clods, and you could crush them into dust simply by closing your hand. Low compressive strength, so they would be easy to process, easy to mine. Oops. Let's see. The volatiles tend to be in the matrix. So these are the different types of meteorites. These are the volatile-rich carbonaceous chondrites. So the higher the percentage of matrix, the higher the percentage of water. Same story with the carbon. Higher the percentage of carbon, higher the percentage of matrix. And you ask, what is matrix? Well, that's a very fine-grained material. It's in physical and chemical disequilibrium, so it was probably accreted cold. That's why it has volatiles. That's why it has water. That's why it has clays. They also contain things like pre-solar grains and all sorts of other low-temperature materials. The volatile-rich carbonaceous chondrites have lots of matrix. Also, the silicates that they have tend not to be high-temperature silicates. They tend to be clays. Clays, again, have hydroxyls, and so they're interesting from a resource point of view. And as you can see, they tend to cluster. When you get clays, you get a lot of them. When you don't get clays, you hardly get any. So what I've been doing lately is I've been looking at developing terrestrial analogs for regolith, for asteroidal regoliths. And this is actually pretty easy because you've got meteoritic material, these meteorites, that used to be on the surfaces of asteroids. And so you can look at their mineralogy and you can develop an analog out of that mineralogy using terrestrial materials, and it's fairly straightforward. You just have these hydrated clays, these phyllosilicates, a few silicates, some oxides, sulfides, and carbon compounds. The carbon compounds are mostly kerogens. And this is fairly straightforward, except for the kerogens. The problem is that meteoritic kerogens tend to be rich in this stuff called polycyclic aromatic hydrocarbons. Now, I had never heard of this stuff before, or only in passing. And it turns out that the aromatic, I wonder why it was called aromatic, and it turns out that this was coined back in the early days of organic chemistry, because one of the tests that organic chemists used to do in the 19th century was they would do color, they would do reactivity of various sorts, and then they would also do smell and taste. As a result, a lot of early organic chemists never lived very long for some reason. They discovered all sorts of things that were very violently reactive to human tissue. Actually, more than 20% of the carbon in the universe is probably associated with these polycyclic aromatic hydrocarbons, which I'm going to call PAWs. And PAWs are basically residuals of high temperature reactions and high pressure reactions. There's a bunch of ways you can get these kind of reactions, but essentially it's residual material. What you've done is you've PAWs have more carbon atoms than they have hydrogen, so you've lost hydrogen atoms. And essentially this is the same sort of stuff that you get on your barbecue grill after you grill steaks or burgers. Some of these high temperature reactions can probably be regolith processes. And so it does make sense that this is the way that carbon and organic compounds are developed on asteroids. And they're a source of carbon. You've got lots of carbon, so you can make methane. You have lots of hydrogen, so you can make water. But you need to be a little bit careful. When I was developing these recipes for asteroidal simulants, I was finding various sources for the minerals, and that's pretty straightforward. Then I called up my contacts in the hydrocarbon industry, and I would ask them if you could get something that has lots of PAWs. And PAWs are type 4 kerogens. And they're in the kerogen business. They should know about this stuff and have lots of it. And my reaction was, their reaction was, are you crazy? Nobody does that. There's no commercial market for it because we would be shut down the next day by the EPA. This stuff is poison. And people who have had that in their products in the past are now Superfund sites. So basically, this is hydrocarbon potential in kerogens. And so oil, gas, mainly gas, none. This is not encouraging. If you look at the individual PAWs, the problem that you have is that the ones that have been well studied are essentially banned. And the ones that haven't been well studied probably will be banned. Naphthalene, that's the active ingredient in mothballs. I have mothballs, it's no big deal. But the problem is that it creates all sorts of things like hemophilic anemia. It's partially banned in California. It's banned in the European Union. Benphenols. This is one of the starting materials for PCBs. It's actually not all that toxic, but it's banned in California. California has initiatives to the electorate. And so somebody put together an initiative about PCBs a while ago. And so biphenyls are completely banned in California. The irony, of course, is that you have this carbonaceous chondrite by the name of Sutter's Mill that landed in California. It's full of biphenyls. If it had tried to come here in a legal fashion, it would have been banned because it has banned materials. Anthracene. This one actually looks kind of bad. It's mutagenic, teragenic, hazardous to skin contact, inhalation may lead to chronic respiratory disease, may cause organ damage. It's toxic to kidneys, lungs, and mucous membranes. Pyrene has a number of problems, targets liver, blood, and kidneys. Chronic health effects are carcinogenic and mutagenic in mammals. High toxicity in animals, highly mutagenic, and its biodegradation products possibly create exponential effects on toxicity. It doesn't sound very good. Fluorethene. It's not very well known, but suspected that it's mutagenic, carcinogenic, and so on. It also has, it's suggested that it has a low flash point and it's somewhat flammable. Anyway, these are PAWs. This is what's in carbonaceous chondrites. It's not like this is terribly toxic stuff. Your barbecue grill is probably far more toxic than any meteorite. However, you just need to study this and keep in mind when you're designing things like EVA systems, like ISRU systems, like any human or robotic interaction with this type of asteroid, which is quite valuable, that you need to remember that you can't go around breathing in a lot of this stuff. You need to separate it from the human component. So you need to keep that in mind for design of ISRU extraction hardware, because you don't want to end up concentrating toxic materials, robotic and human operations. Any experimental design. I've been talking to a lot of people who want to work with asteroid simulants, and they also want to work with small amounts of meteoritic material, and I ask them, if you're going to be distilling your carbonaceous chondrite and trying to get the volatile and carbonaceous and organic materials out of it, do you know that the organic materials are toxic? And none of them did. So that's one of the reasons why I'm giving this talk. You need to be a little bit careful. This is hardly the worst thing in any lab. It's actually pretty safe. You know, meteoriticists have been handling this stuff for decades, and I have not observed any increase in the death rate of meteoriticists. In fact, meteoritists tend to be very long-lived. There are those in the audience that have been handling carbonaceous chondrites for decades, and you're still around. So you just need to be a little bit careful. I would recommend against, dry cutting of your carbonaceous chondrites in your lab and filling it with carbonaceous dust. But anyway, this is not terribly onerous requirements to be a little bit careful. It's just you should be a little bit careful. And when I'm looking at this and developing engineering chemical analogs for asteroidal material, and although I would like to get as high a fidelity as possible, I will not put things that have pause in the simulants because I want to be able to get them onto NASA centers. So anyway, thank you very much for your attention.
Thank you, Dan. We have time for some questions.
Oh, I'm finally glad to hear that you came out of the closet and admitted that you had mothballs.
Larry, you have no idea about all the dangerous stuff I've done in my life.
Roslava Bonacorsi at Institute. I'm very curious about several things. I have 3 questions. One question is, I understand correctly that the path to the IDPS comes through all bodies, including Earth's surface, and therefore they should be encapsulated in the carbon cycle in terms of toxicity, or?
Well, I think that people need to develop some way of isolating this stuff if you're going to do it in any large amount. And you don't want it to end up in your recirculation system in your space capsule, for instance.
Yeah, and the other question is that if this stuff is present on Mars, I'm assuming they should accumulate. And these are already residues. Why they are not found by pyrolysis?
Well, I'm not a Mars person. And so I think people have found organics on Mars, or have they? I don't know.
Tiny
ppm,
amounts.
But remember that you're talking just a few weight % in meteorites. Mars is differentiated, so you're going to accumulate meteoritic material, but you're in an environment of that's fairly reactive on the surface. So it might very well that the stuff reacts out to something else.
Yeah, there was understanding that path through the cosmos would be subject to a lot of weathering processes too, so they are kind of residual.
Yeah, I don't know.
Okay, cool.
They exist on meteorites. That was my interest. I'm not a Mars expert.
Cool, thank you.
You've just discovered one of the many things I don't know.
The peroxides and UV are likely to break that down.
Yeah.
Break most of those down into carbon dioxide.
Yeah.
I would think.
Yeah, I think that's a reasonable supposition.
Dan, I was just curious your perspective on whether you were more likely, for your longevity prediction for your previous career in a missile silo versus a meteoriticist.
Meteoriticists are a lot less well armed than the major. Toxicity. Yeah, well, Toxicity, actually the major risk in missile silos is that you're surrounded with teenagers with machine guns. They're called troops, but they're still teenagers with machine guns. I found that very scary.